Yo. What's up? Welcome to another Zozin offline stream. Yes. So today is Tuesday, if I'm not mistaken. I think today is Tuesday. That means today, according to the schedule, we are developing BM, which is virtual machine plus programming language and stuff like that. The status of this project is actually rather complicated, I would say. It also has a very complicated history. Right, it also has a very complicated history. So this project started with something called eBisp, embedded Lisp. And essentially this is just a Lisp interpreter as a library. And it has the same goal as Lua, for instance. It's supposed to be like a scripting language that you embed into your application to extend it with scripts and stuff like that. So at some point, I decided to implement a bytecode for this language. I decided to implement a bytecode for this language, and this is how BM was born, right? This is how BM was born. So the idea was to actually, in an interpreter, in an eBisp interpreter, compile the Lisp code down to BM bytecode and then interpreted it on BM. But then, as I developed BM more and more, I added a very interesting thing that is called Bosom, right? So it was supposed to be like a small intermediate language, like temporary language, to basically write BM bytecode in a more human readable way. And this development of that language actually caught me up so much that it turned into its own thing, right? And now like Bosom, the assembly for bytecode of the BM, actually looks like this. Yeah, it's essentially turned into a very powerful language with the metaprogramming capabilities, and it has scopes and like compile time variables and stuff like that. And I thought I'm gonna continue developing BM in that direction, completely forgetting about eBisp. And the idea for quite some time was that let's have an assembly, but on top of assembly, let's put a very powerful metaprogramming language. And basically your programming is going to be consistent of generating this assembly. So essentially with metaprogramming capabilities, you would be able to start in a very low level and then build up abstractions as you need, going higher and higher in the level, and then you're going to be programming in a higher level language. So it was an interesting idea, and it was going, you know, relatively well, I suppose. But again, I wasn't sure if that was a good idea. I wasn't sure if like the idea of taking like a low-level assembly language and just putting like more and more powerful metaprogramming capabilities on it is generally a good idea, and that's why I was implementing it. And after some time, I can see that it's an interesting idea. Developing this entire thing is pretty cool, but I still cannot tell if it's a good idea or not. I still cannot tell if it's a good idea or not, because over time this entire thing becomes very obscure and very complicated. So yeah, I'm not sure if it's a good idea, to be fair. But it turned out that actually very powerful. This application that you see written in Bosom actually interacts with SDL, and if you follow the development of BM, you probably saw this example. So examples run SDL. So, and this entire example is written completely in Bosom. Right, and the window is created using SDL and stuff like that, but the whole logic, the whole animation is written in Bosom, and it's pretty powerful, not gonna lie, it's pretty powerful. And since you can now hook up C libraries, you can make it even more powerful and stuff like that. But yet again, I'm not sure if language itself turned out really that great. So here's my idea. So today is going to be a very pivotal stream for the development of BM, because I'm abandoning the idea of Bosom. I'm not really abandoning Bosom per se, so Bosom is probably going to stay in some form as part of the project, but here's what I'm going to do. So we already have a virtual machine, right? We already have a virtual machine called BM, right? And on top of BM, we implemented Bosom, which compiles down to the virtual machine bytecode. That's what it does. And what's cool about this bytecode is that it's written in a very portable C. What's interesting about that virtual machine, not bytecode. So this virtual machine is written in a very portable C. So if you compile your program into that bytecode, it will work anywhere where you can port the emulator of that virtual machine. And we already managed to port it on Linux, Windows, Mac OS, FreeBSD, and this is the only ones that I'm aware of. So basically your program may work on all these platforms. You know, the same benefits as JVM claimed to have. And on top of that, we recently started to actually create converters of the bytecode down to x86-64 assembly. So you can have native executables. So since I'm still not sure, after so many months of development, I'm still not sure if Bosom is a good idea, I'm gonna just put it on the back burner, right? And let's try to implement a proper programming language, right? That also compiles down to the bytecode of BM, right? And what's interesting is that we can continue like developing, we can start developing this language inside of the code tree of BM, right, as part of the toolchain. So in the toolchain, we have a lot of different things. We have Bosom itself, we have the debugger for the Bosom, we have emulator, we have the tester, a thing that actually runs the tests, and so on and so forth, disassembler, and some different tools to actually generate dot files for graphics and whatnot. We can add a compiler for our new language here. And let's just try to implement like a proper language, proper imperative language that compiles down to BM, and let's see how it goes. So that way we can reuse the execution, the runtime environment that we already have. And furthermore, we already have a lot of interesting things in terms of like parsing written for Bosom. So maybe we will be able to even reuse the parser of Bosom in our new language, right? So maybe this is one of the things we'll be able to do. So developing this language inside of the code base of BM enables a pretty good code reusage, I think. I think it enables pretty good code reusage, and maybe it's not going to take that much time developing this language, because it's pretty much going to be the part of the project. So basically we're trying to stir the project towards like a proper programming language and not just assembly with the powerful meta-programming features, whatever the fuck is that supposed to mean. So that's pretty much the idea. So, and the question is how we're gonna call this language, right? Since we basically follow the meme of replacing letters with B, so BM, VM, so we replaced V with B. So for assembly we called Bosom. I don't know, maybe the language that we're gonna develop on top of BM is gonna be called Bang, because we replaced L with B. Ahaha, funny meme. B, yeah. Press B in the chat. Press B in the chat. All right, so yeah, that's pretty much the plan for today's stream, and let's get started. Nothing much to say, because the idea of Bosom doesn't really go anywhere, so let's try to go in the other direction. Let's just develop like a proper imperative programming language that compiles down to BM. And let's see how it goes. And also, it will be interesting experience for me because I never developed these kind of languages. I developed interpreted languages before, but I never developed like proper statically typed compiled languages. So it's going to be very interesting for me. Is the Discord in trusted only mode now? Yes. Okay, so let me find Ivanhoe. Okay, so since I know who you are, I'm gonna give you a trust. So yeah, there we go. So trusted you. Okay. Okay. All right. So what we're gonna start with? I think we're gonna start with actually adding the executable for the compiler. You are welcome. All right. So the executable for the compiler, we're gonna put it in the toolchain. So the executable is gonna be called bang, right? So and it's gonna be bang c stdio, and let's just create an executable. Nothing particularly special. We'll also need to be able to parse command line arguments. Let's try to compile this entire thing. Maybe let's put something like this. Bang, bang. Okay. And I want to put a new line in here. And let's try to recompile. As far as I know, if you have a C file inside of a toolchain, it will be automatically picked up by our build system and create an executable for you. Let's actually test it out. So it's going to be something like this. So, and as you can see, it already throws warnings, so that means it managed to pick it up, which is kind of cool. Let's see what else do we have in here. All right, so let me see if we have an executable in the build folder. Where is the build folder? It's kind of hard to find. So toolchain, here are the executables, and here is the executable. Nice. So, and then if I run it, it says bang bang, motherfucker. Yes. All right, so now we probably need to parse command line arguments and accept at least something. Right, we need to accept at least something. I think it's going to be similar to bosom, right? In bosom, if you take a look at the usage, you essentially just provide the input, right? You just provide the input and it creates an output with the same name, but with a different extension depending on what is the target, what is the output target, right? We have 3 output targets right now. It's BM bytecode, NASM Linux x86-64 assembly. It's assembly, not native code, by the way. You do need NASM compiler to then compile this thing to a native executable. And also NASM FreeBSD x86-64. It was recently submitted by Hotzenplotz. So basically the main difference between Linux and FreeBSD is just like different numbers of the syscalls, but the actual assembly is pretty much the same. It's just like as Hotzenplotz noticed that it's just sysv x86-64, and it's just like the syscall target is just basically different thing in here, right? Nothing particularly special. Nothing particularly special. All right, and maybe we're gonna have a similar situation here as well. So, and maybe we also need like include paths, but we don't need, we don't really have any include paths system because we don't have any module system for our language. Our language doesn't exist yet. We started to develop our language 13 minutes ago, so it doesn't have anything, right? So, yeah. The only thing our language is capable of doing is just printing bang bang to the standard output, which is already something, which is already better than some other languages out there. So let's actually implement something like usage. So this is going to be like a stream where we're going to print the usage, and in here we're going to print something like stream usage, and it's going to be bang. Maybe it's just going to be just bang, and this is going to be options. We're going to have a bunch of options in here, and you're supposed to provide input with the extension bang. All right, and the question is, what are the options? Of course, I forgot a new line in here, right? So the options are the following. So I suppose for now, what we want to have is probably something like -h. So what is the usual padding that we use in here? Like the padding is like 4 characters, 1, 2, 3, 4. So this is the help, and print this help to std out. Okay, so let's do it like this. Print this help to std out. Right. So far we're gonna have this. Do we need to have anything else? We could do something like stream O, and O is usually something like output. Provide output path. Okay, provide output path. All right, so this is what we have in here. So what I usually use for, yeah, I usually use a function called shift for parsing command line arguments. It's actually a very interesting function. Believe it or not, it is in fact a very interesting function, and the easiest way to demonstrate this function is probably just use it somewhere, like essentially while argc is greater than 0, what we're doing, we're just doing printf as shift argc argv. So that's the simplest usage of this function. So I wonder where it is defined. I think it's defined somewhere in the library. So let me actually find it. It's going to be something like shift. And I can see we are in a tool chain, but I should have actually, okay, let me grab shift. I feel like I actually re-implement this function in each individual. Yeah, it's such a small, simple function that I'm kind of like, I don't know where to put it. So I sort of like re-implement it in each individual executable. Like I just don't know. It's very small and simple, but yet it's actually super powerful for parsing command line arguments. Look. So let's just recompile everything, and it's going to be no build test, right? So here it is, no build test, and it doesn't even work. So let me see. So there's a couple of warnings in here, because printf is supposed to be fprintf if you want to supply the sink where exactly you're going to output things. And do we have anything else? Do we have anything else? So we have assert equal 0. So, but it is equal 0, so otherwise it wouldn't work, would it? Oh, implicit. Oh my god, I'm an idiot. So it's just a warning saying that I don't have an assert. Okay, I think I just need more tea. Okay, and then here, so this thing, no previous prototype for usage. Okay, so we have to mark it as static. And this thing is never used, but that's fine. That's fine that it's never used. Okay, so our code looks like this, right? We are iterating while argc is greater than 0, and what we're doing in here, we're just shifting argc and argv. So, and then let's just try to run it and see what's going to happen. So if I try to run it, it's called bang. It's actually toolchain bang, right? So what it does, it just prints its own name, but we can also provide other things, full bar, buzz, and so on and so forth. So it's printed its own name and the command line arguments. So shift enables you with basically iterating command line arguments. So the thing it does, it sort of pops out the command line argument from the left of the argument list. Right, and what it does, it automatically updates argc, decrementing it by 1, and argv, incrementing it by 1. So that's essentially what it does. So it is actually kind of similar to shift of bash, right? In bash, you have a shift function, actually command, or yeah, I think it's command. And essentially what it does, this command takes one argument, a number of the positional parameters. So it's not really what we do, but essentially it just, you have command line arguments in the form of $0, $1, and so on and so forth, and you shifting them, and it shifts them like by 1, right? And that way you can actually parse command line arguments in the shell. So essentially what I I implemented the shell shift in C. As far as I know, it's not only exclusive to bash, it also exists in Perl. But yeah, that's essentially what it is. That's essentially what the shift command is, and it actually makes it super easy to parse command lines, and you will see how, right? Because it's sort of like you can just always query like next argument please, next argument please, and at any point you can say, oh, I ran out of arguments, I better throw an error when I do expect an argument here. So yeah, that's essentially what it is. Does it make sense? Hopefully that makes sense. But I primarily use this command now for parsing command line arguments in C. These days at least. So maybe I'm gonna put this kind of thing in the description. shift command O bash. Okay, so this thing is going to be something like this. This thing is going to be something like this. And let me see. Okay, how are we gonna parse all of that? So I want to kind of skip the shit. Nice one, Zozin. Shift argc argv to skip the program, because the first argument in the command line argument is the program name. Skip program, but we don't necessarily have to skip it and completely ignore it. One of the things we can do, we can actually save it, right? So this is going to be like a program, right? And then in the usage, we can accept that program in here. And then we can like use it as the parameter. So depending on how it's called, it's going to have a different name in the usage. Why not? I think it's a pretty useful thing to do in here. All right. So what we expect as an input in here? Well, we expect input file path, right? We expect at least input file path, and initially is going to be null, indicated that no input file path is provided yet. So then we can have output file path, which is also null, to indicate that nothing was provided yet. And I guess that's pretty much it. We don't really need anything else. So let's start iterating these things. While argc is greater than 0, we're going to be extracting the next flag, right? So this is going to be the next flag. argc, argv. And what kind of flags do we have? We have -o and -h. All right. So if strcmd flag is -o, right, what do we do? That means we encountered the output file path. So what we need to do now, we need to check if argc is greater than 0. And if it's not greater than 0, if it's equal to or less or equal than 0, because argc is integer, so it can be negative, right? Who knows what can happen. If there's no parameter for this flag, we are going to actually throw an error. But first of all, we can probably want to actually print the usage, and we're going to print it to std error with the corresponding program name, because we do have a program name. Also, we can mark program as constant, because I do not plan to reassign this program. This program is going to be assigned only once. And by the way, this const is not enough to make this program non-reassignable, right? So that's why you need double constant here. Well, I mean, it's actually not really obvious, especially for people who only learn C, but I can demonstrate what exactly I mean in here. So if we have something like this, right? So it's going to be stdio, and it's going to return something like this. And imagine that you have something like s hello world, right? You have something like s hello world. You cannot modify any of the characters in here, right? You cannot modify any of the characters. This stuff won't compile, right? So as you can see, you are trying to assign a character to a read-only location, but so it's a pointer to the const char, but the pointer itself is not const. You can still reassign it to something else. You're not modifying the string. You're not modifying any characters of the string, but you're reassigning the variable to a different kind of string. So to make it both non-modifiable and not reassignable, you have to have two constants here. Right now, you won't be able to do any of these things. So that's why I have double constant here, because I just got the program. I do not plan to modify the name of the program, and I do not plan to modify the contents of the program. So yeah, like I might as well just mark it const to let the compiler that none of these things are going to happen. But to be fair, these days compilers are pretty smart. They can figure that out by themselves. They can just see that, oh, that user does not modify any of these things, so this thing is pretty much constant and not modifiable, and I can just make a lot of assumptions about that and just optimize things accordingly. So, but in any case, I just want to do that for myself, and if I try to do something weird, I want the compiler to warn me about that. See what I mean? Does it make sense? Maybe. I don't know. All right. So this one is going to be error. No value is provided for flag, and we can just put this thing like that. And after that, we probably want to exit with 1. So if this condition didn't fire up, that means we do have a parameter for this thing, and we can do something like output file path, shift argc argv, and there we go. So you have a output file path. All right. The next flag that we want to check for is probably something like -h, right? And if you encounter this specific flag, we're gonna just simply output the usage to the standard output, and then exit with 0 exit code, because that's precisely what the user asks for. All right, if we encountered an unknown flag, we're gonna treat that unknown flag as an input, right? We're gonna just treat it as an input, and essentially we're gonna just do input file path equal to flag, right? So that is it, pretty much. That is it. So after that, we can check if input file path was provided. If input file path was not provided, we have to scream at the user, telling them that, bruh, what the fuck? So what we're gonna say in here is std error, error, no input file path was provided. Right, and then we're gonna just exit with 1. So here's an interesting thing. If no output file path was provided, we need to like derive the output file path from the input file path, right? So for instance, we have to strip off the bang extension and put our own extension. And I think this is precisely what we're doing already in Bosom, and I think I'm gonna steal that code from Bosom, right? So if output file path is equal to null, what we have to do, let's steal that code from Bosom. So yeah, there we go. So we this one is interesting. Okay. So output format file extension. So we have a function called file name of path, and it is defined. Oh, we have a special library that is capable of stripping off the extension from the file path. This is actually pretty cool. I really like that. But it requires yeah, after that we'll have to concatenate this entire thing, but concatenation requires allocations, and we usually do all of the allocations via the arena. So arena allocator, right? So here's arena allocator. If you never heard about this kind of style of memory allocation, check it out. So let me put the link for you in the description. Region based memory locator arena, and here is the link to Wikipedia. Also, I recommend to take a look at the original paper about the arena locations. That is basically I don't know what was the original paper though. There was like a PDF for it, but I think, yeah, I think you can find a PDF for this paper somewhere on the web. I don't know. Don't pirate though. Pirating is bad. Anyway, so let's continue. It's gonna be in the description just for you. Okay, so let me see. We take the input file path and we strip off the extension file name of path, and then we probably need to allocate arena somewhere. Probably need to allocate arena. Let's actually put arena somewhere here. Right, so this is going to be arena. As far as I know, arena doesn't really require any initialization. You can just allocate the structure somewhere in 0, initialize it, and this is going to be a valid arena. You don't have to do anything with it. Let me take a look. So it's going to be arena.h. So yeah, you can allocate things within the arena. And it consists of only 2 pointers on 2 regions and stuff like that. I think I will have to include the arena in here to be able to use it. This is precisely why I'm not starting this language from scratch, because inside of BM we already have a lot of these like tools implemented that we can just reuse. So we have already a string library, the memory management library, we have Tokenizer that we're probably going to reuse. Tokenizer is actually quite good in here. Maybe we can reuse parts of the Parse and actually get this thing going faster than we would have if we started from scratch. So that's precisely why I don't want to start from scratch, because we have a lot of cool stuff in here that we can just reuse. So yeah. Anyways, so this is arena.h. And after we're done with arena, I suppose we need to do something like arena free. Right? So let's not forget to free the arena. Free. After that, output format file extension. This one is weird. Yeah. So it just depends on the output format. We don't support several output formats yet. So I think it's easier for me, like it would be easier for me to simply just do something like this. All right. I'm gonna concatenate this entire thing with just simply BM. Right. We're just concatenating everything with simply BM. And all of that is supposed to be a string view, so I probably have to do something like this. There we go. So, and here we have output file path, and after that I want to convert it back to sister, because a lot of the function that read from files, they accept C strings instead of string views, unfortunately. So that's precisely what we have to do in here. Output file path is going to be equal to that, and I think we're ready to go. So I'm going to put it like this, and now I think I'm going to just output the following thing. Input file path. Input file path is going to be S. Input file path, and this one is going to be output file path, and there we go. Let's try to run this entire thing and see. Well, first let's try to compile this entire thing. Yeah, I think this is not how I'm supposed to compile it. I'm supposed to just run no build test. All right, so we don't have a bosom arena, we just have arena. And we still have some warnings in here. Implicit declaration, this is because we probably need to include the path to be able to work with paths. So you see, we're reusing things from our main library, from our main project. And this is quite convenient, not gonna lie. Okay, so now I can do something like bang. It's actually part of the toolchain. Bang. Okay, so as you can see, nothing is provided. I can now provide something like main bang. And as you can see, input is main bang and output is main.bm. So it automatically derived the output file path from the input file path. But we can always change it. We can always say something like full bm, right? And as you can see, it will work. So it's pretty convenient. It's pretty convenient. But by default, you don't have to provide the output file path. It's going to be derived from the input file path, which is quite convenient, which is precisely how majority of the compilers works anyway. All right, so the next thing we need to do, we need to be able to read that file. All right, so the input file path is provided. We need to be able to read it somehow. Well, luckily, arena function provides a pretty convenient function called Slur File. Yes. It provides a slurp file, which essentially just slurps the entire file into the arena and just gives you the pointer to the string view. And then you can parse this entire thing and process it and whatnot. So this is precisely what we're going to do next. We're going to slurp the entire input file. Just slurp the entire input file. So we're going to provide the arena because arena is going to be used for allocating the memory for slurpage. And then we need to provide input file path. As far as I know, input file path is a sister, but arena slurp file accepts string view. So we need to convert string view, actually sister to string view. Let me see. sv.h SV from, yeah, here it is. I can see that. So where is the sister? 15 down. Okay, so this is the function I need. Not the function I deserve, but the function I need for sure. For sure, for sure. Okay, so here we go. We're gonna store the content in here. So here is the content. All right, I'm going to provide the pointer to that content, and there we go. So this entire thing, as far as I know, can return like a negative value if something went wrong, and in that case we want to print an error, right? So first of all, do we want to print a usage? I don't know, maybe not. So it's going to be std error, error could not read file as because this shit happened. So in the file that we couldn't read is the input file path. Right, and the reason is located inside of the error no, and then after that we can just simply exit with 1, and there we go, there we go. So the thing I want to do now, maybe I can just output this entire thing into a different file. Or maybe I can just print it to the standard output. I think it's going to be easier. So I can do something like printf svfmt. Then svarg, and yeah, I'm just printing it to the standard output just to see if we manage to read the entire thing. So, but we need to actually write it first, right? So let's actually write our first bang program. So it has to be something like main bang, and the question is, what kind of syntax is it going to have? I don't know, let's write something simple. So we need a keyword for defining function, and this is where chat always goes crazy because it's I'm asking about the color of the bike shed, right? It's very easy to have an opinion on what's going to be the keyword for defining a function, but bike shed is going to be red, so the thing is going to be prog. Okay, whether you like it or not, feel free to hate me for using this keyword. I know I'm a horrible person. Yeah. It's easy to have an opinion on the color of the bike shed. Anyway, so this is how we're going to define the function for now, at least. And what we're going to put in here, 1, 2, 3, 4. Let's actually write a hello world. Let's try to compile and make a hello world down. Why did I put down there? Let's actually start with just implementing enough compiler functionality that can compile hello world down to the BM bytecode, and when we run that BM bytecode, it should actually print hello, right? So this is going to be like a hello world of the compiler. It's actually kind of interesting. Hello world of a compiler, which only can compile a hello world program. That's very interesting. That's very interesting. But what's cool is that our virtual machine is already capable of printing hello world. That's what's cool about it. So I can do something like main bosom, and in bosom it would be something like you have to specify the entry point 1, 2, 3, 4. Then you have to push hello world into here. You might as well actually. It will be better to put it into a separate variable. So let's put it like that. So this is going to be hello. So later you can also push the size of that hello, and then you can call a native function write. But as far as I know, yeah, you also need something like this. A native function write. And then you can hold this entire machine. So this is how much code it takes to write a hello world in our assembly for the virtual machine, but in our language, hopefully it will take this amount of code to write a hello world, right? We won't need to pass a length because maybe the length of the string is going to be attached to the string itself, right? Who knows? We'll see. All right, so, and I can demonstrate that this entire thing works. I first need to compile it down to BM. So if I run something like build toolchain bosom, and it's going to be main bosom. And did it work? Did it work? I think it worked. So here it is. And if I try to now run this entire thing, it says hello world. Would you look at that? Yes. So our virtual machine is already capable of doing these kind of things. It's just a matter of taking this source code and translating it into the bytecode of the virtual machine, and that means our languages will be able to do this kind of stuff. All right, anyway, so we already do what? It's going to be bang.c. So we already can slurp a file and we can print the content of the file. Did we already compile this entire thing? Let's see if it's compilable or not. So it's going to be something like this. And it's not compilable. And this is probably because I need to include error no. And also strings and stuff like that. So it's going to be string. Okay. So build toolchain bang, and it's going to be my main bang, and as you can see, it printed the content of this file. So our compiler is already capable of parsing command line arguments and also reading from files. Isn't that cool? I think it's quite important to have this kind of stuff in the compiler, because one of the phases, one of the steps that compiler does is reading your file. It's kind of difficult to implement a compiler in a modern hardware without being able to read the file. So I think being able to read the file is a very, very important feature of any compiler. And I say that unironically. So let's go. What else are we going to have here? So the next step after reading the file is usually tokenization. We already have a tokenizer for the bosom, right? So maybe we can reuse it actually. That's actually very interesting. Can we reuse this tokenizer? So these are the tokens that we can parse. Maybe for our language we're gonna add more, but for now I think these tokens are all right. I do think they are all right. So to start a tokenizer, you can construct a tokenizer from the string view, and we do have a string view for our content of the file, right? So we do have it. So let's provide the content, and there we go, we got a tokenizer. All right, so next thing we need to do, we need to constantly query the next tokens, right? We need to constantly query the next tokens. So we're going to provide the tokenizer in here, then we're going to provide a pointer to the token, right? And we have to allocate that token on the stack, right? And file location, we don't really have a file location. I just realized that. I would expect the tokenizer to, you know, generate a file location for me, but it looks like it's not really easy to do that. Okay, so do we have any constructors for the file locations? We don't really have any constructors for the file locations. Maybe we need to implement one. Why not? So let's create file location, and in here we're supposed to have something like a string view, file path, and in here I don't quite understand why Tokenizer has a file location. It's probably for reporting errors. Yes, it's probably for reporting errors. When you encounter an unknown token, the Tokenizer will report an error saying that I don't know this token, bro. So, and yeah. So maybe we'll have to do a little bit of refactoring to decouple the Tokenizer from reporting errors somehow. So I don't think Tokenizer should report this kind of errors themselves, but we'll see. It's kind of an interesting thing. So of course some of the things needs to be reparsed, refactored after we you know, moving our development to a completely different direction. So file location is a file path, and it's going to be int line number, right? Int line number, and maybe we don't even have a C file for this thing. Okay, we don't even have a C file. fl.c, fl.h. Actually, we need to include h in here. Right. So we're including the h. So in here we're gonna just simply construct this entire thing. File location. There we go. This one is gonna be file path. This one is gonna be file path, and this one is gonna be line number. Right, so this one is gonna be line number. Okay. So the next thing is going to be what? So let's actually construct some sort of like a dummy file location, right? So dummy fl. File location is going to be something like a file path. It's going to be input file path, and it's going to start at the 0 line or something like that. So this is going to be a dummy file location, and essentially what we're going to be doing, we're going to be iterating while we do have the next token, and we're going to be just printing the tokens. I wonder if I can take the token type, right? If I can take the token type and print it as a name. So as you can see, I have a token kind. It is called a token kind, and looks like I can print this entire thing. So we extract a token out of that stuff. Okay, this is actually very interesting. So maybe this is precisely what I wanted here. So I'm gonna have like, oh, I would like to actually print file locations in front of each individual token, but with the current code, it's not going to be possible, unfortunately. So we'll have to do something else. It's going to be token FMT, right? And then I'm going to provide like a new line in here. And this one is going to be token arg, and in here is going to be token kind, right? So maybe just token, right? So I'm trying to print the token in here, and that should actually print all of the tokens or fail, saying that I don't know about this token, right? And I'm pretty sure it's gonna fail because we never had this kind of token before, right? We never had this kind of token before. All right, so let me see if we can compile this entire thing. So it's going to be no build test, and so what do we have in here? String view. Maybe we need to include sv.h for this thing to work. And is it going to be working? Is it going to be working? All right, so we also need a tokenizer, tokenizer.h. And is it going to compile now? Input file path. Okay, so this has to be a string view, so we have to do something like sv from system, right? So this is going to be sv from system. Is it working now? Hopefully. Okay, it seems to be working. Cool. Now let me try to run this entire thing, and it's going to be something like build tool chain bang, and it's going to fail because we have one unknown token in there. Okay, so we got name open parent. Oh, okay, I see what happened. It recognized proc as a name. Right. Let's actually print the values of these things as well. I think it's going to be beneficial. So here we're going to have something like, I suppose like token kind, right? And in here we're gonna have something like this, and we're gonna wrap it into quotes, right? So this one is gonna be token kind. Is that what it's called? Is it not called token kind name? Okay, I think it is called token kind name, right? And then it's gonna be token text, and because of that I think we'll have to use svfmt, right? It's gonna be svfmt and svarg. There we go. And if I try to, I also need to recompile this entire stuff just in case. Okay, so overall, as you can see, it seems to be working. So proc was recognized as a name. A main is a name. We do have open parents. We also have closing parents, but we don't have curly braces, right? So that's one of the things we don't have yet. But maybe that's precisely what we need to add. So I think this is the only thing that we'll need to add here, because this thing will be recognized as the name, and then we have parents, and we also have string literals as the tokens. So it will be tokenized properly, hopefully. We'll see. So let's go to the tokenizer, right? Let's go to the tokenizer, and in the tokenizer, we're going to add all of these things. I'm going to sneeze, by the way. All right. Okay. So this is going to be token kind open curly, right? So this is open curly, and we're going to have a closing curly. I wonder if this is enough to trigger compiler to tell me all of the places where I need to make the changes. So we have a couple of places in here. So primary expression. So this is for the parsing, right? This is for the parsing, and I think for now none of the primary expressions start with curly. Open curly and then closing curly, right? So what else do we have in here? So token name. Okay, so we can have a similar thing. Why there's so much inconsistency in here? Why can't we just use the same stuff in here like that? I don't know. Kind open parent, and here we're gonna have curly. This one is gonna be something like this. And is it going to work now? All right. Okay, and we have a known token starting, and it still didn't work. What the hell? So, oh yeah, so it's not enough to actually add. Okay, I see. Oh boy, oh boy, oh boy, oh boy. So in the tokenizer itself, we also have to look into all of these things. Yeah, it's a classical problem in here. Yeah. So maybe, can we use static assert to actually tell this thing to assert all of them? I'm not even sure if we can. But yeah. Not even sure if we can. Okay, so let me now try something like this. And this one is going to be open curly, right? Curly. And there we go. Let's try to recompile this, and I think hopefully this thing will work now. And now we managed to tokenize the whole program. Would you look at that? Yes. So the original program, as you can see, this is not it. Actually, this is not it. It looked like this, and here are the tokens of this program. So we are already capable of tokenizing everything. Though we are incapable of tokenizing this keyword, and I wonder, do we want to add it right now or do we want to add it later? If we add it as a token, this token, since the tokenizer is shared between Bosom and Bang, this token is going to be available in Bosom, but I mean Bosom doesn't know how to parse it anyway, so maybe it's not going to be that big of a deal. So it will still, like if you try to use this token in Bosom, it will pass the tokenization phase, but it won't pass the parsing phase, right? Because none of the Bosom parsers actually handle any of this thing. So because of that, I think it would be fine to actually add this token there. You know, maybe before I'm gonna start adding these kind of things, I wanna create a separate branch. Let's call this branch Bang. So what did we add in here? So do I need to add anything else in here? Probably not. This is a garbage. It's not needed. Add Bang language compiler to the toolchain. Right. So this is going to be our thing. I'm not going to push it right now, just to not spoiler anything for people who follow me on GitHub. And let's go to the tokenizer. Let's go to the tokenizer and add proc or something. So it's going to be token kind proc. Here it is. Token kind proc. So in how many places this thing needs to be changed yet again? Case token kind proc. I feel like trying to reuse the code between Bosom and Bang is going to create a lot of confusion. But I wonder if it's going to be a lot of confusion at first, maybe later over time is going to be better. And another question is that, do we want to maintain Bosom? As Bang compiler grows, the reusage will become more and more infeasible. So at some point we'll have to drop the Bosom support or something. Another interesting idea I have is that we can actually make Bosom a part of bang, right? We can have an inline assembly, right? So maybe something like BASM, and then you will be able to just push things like 1, 2, and plus I, or something like that. I don't know, and then just like let X or whatnot, right? So maybe at some point we'll just make a BASM a part of the bang, and that way BASM is going to be completely obsolete, so we won't need this kind of thing. Yeah, who knows? Who knows? We'll see. So let's just continue development, and maybe it will make sense a little later. So we have this thing in here. I need to copy paste this stuff. So this is going to be proc. It's going to be proc. All right. So everything seems to be okay, but it was never actually tokenized properly. Right. So we want to go in here and else if sveq token text sv proc, right, sv proc, and this one is going to be just a proc. There we go. Is it going to work now? Hopefully. We'll see. Yep, there we go. So we have a proc, we have a name, and now we should be able to basically parse this entire thing somehow. The question is how. We need to introduce the AST. I don't think I'm going to reuse the AST from BASM. The only thing I'm going to reuse is a tokenizer from BASM. I don't think a BASM AST is reusable at all. All right, so what do we even have in here? In terms of like AST? We have a procedure definition. So here is the procedure definition. Inside of the procedure definition, we have a name of the procedure and an argument list. So right now, our argument list doesn't even have any arguments. So maybe we're not going to implement the argument list in AST at all. Then the procedure has a body, which is a sequence of statements. And one of the statements in here is, a function call, right? One of the statements here is a function call, and maybe these things are going to be separated by semicolons. Can we even tokenize semicolons? I think we cannot. We can't even tokenize semicolons. Let's actually add semicolons to the tokenizer then. Token kind semicolon. There we go. And let's just go through the entire thing and add this thing to the tokenization phase. So none of the expressions start in here. So this is going to be semicolon. So in here, we're going to just have a name for it. Semicolon. This one is going to be something like this. And that is it, but except we also have to add this entire stuff in here. KGB. So, all right. KGB is after me. I'll probably have to throw away that phone at some point and buy a new one because they already know my new phone. New phone number. All right, so let me actually replace this thing with semicolon, and it's going to be semicolon like this. And let me try to recompile this entire stuff. All right, everything seems to be working, so we can tokenize this entire thing now. Pretty pogue, is it? Is it not? Pretty pogue, is it not? Add more tokens for bang. Right, so we just added more tokens. All right, so let's actually start working on the AST. But before we go and work on AST, I think I want to make a small break because I'm already streaming for like 1 hour. I'm getting a little bit tired. I want to make a cup of tea and so on and so forth. So, yesu. Kawaii fucking desu. The goal of today's stream, by the way, is to have a compiler, right? Is to have a compiler that can take this program and compile it to something that outputs hello world, right? So we are speed running the compiler development. Yes, that's what we do. So I wonder how difficult it would be. Shouldn't be that difficult. If you think about it, shouldn't be that difficult. The main problem is probably like how do you represent the body. Body should be like a bunch of statements, and each statement, one kind of a statement that we can have right now is basically an expression, right? An expression that performs side effects. So we just need to take some time to basically outline this entire stuff and then implement a parser that just takes the sequence of tokens and just turns that into AST. Pretty straightforward. And after that, once we have an AST, we can traverse this AST and turn it into the bytecode, hopefully. Anyway, I wanted to make a small break, so it's going to be like around 3 minutes. We're going to listen to some music. All right. Okay. DMCA incoming. By the way, literally all of the VODs, all of the offline streams that I upload to YouTube, they always get a copyright claim because of the breaks. So I can actually probably get rid of the copyright claims completely and maybe at some point monetize this entire channel if I were not so lazy. Just couldn't give a shit. Sorry. Anyway, so let's make a small break. Can you guys have fun? Yo, I'm back. Champion of the arena. Ooh. Alrighty. So we need to start working on the AST. So, what we're gonna have in here? So how we're gonna, well, let's actually start with like defining the things that we have in there, right? So we're gonna have something like bang proc definition, right? So that's what we have in here. We have a bank proc definition, and the proc definition is basically this entire thing, right? This is a single procedure definition, right? So, and what procedure definition consists of? It consists of the name of the procedure. So we can literally call it just name, nothing particularly special. It also consists of the argument list. But since we don't have the arguments for this specific example, maybe we wouldn't care about this entire thing at all. Right, so next thing it consists of the body, right? So let's actually introduce the body, but the question is, what's the body gonna be? The body is probably gonna be some sort of a block, I suppose. Let's call it like something like bang block, right? So the question is, what's the block? What's the block? What's the block? Block. Bang block. What's the bang block? It's a sequence of statements, right? So it's a sequence of statements. So I suppose we're gonna have something like bang statement. It's a bang statement, and then since it's a sequence of them, we can make it like a linked list or some sort of like block next. Because like creating a linked list is going to be easier when you like sequentially parse everything. Right, so we're going to have something like that. Bang statement, bang block next. And I suppose maybe since it's like it has a next thing in here, maybe the body itself has to be a pointer too, indicating that maybe proc may not have a body. Or maybe it could be an empty body. I guess, yeah, if you have an empty body, you need some sort of an indication of that, right? If you have proc f this, how do you indicate that? Well, block itself has to have at least one statement. Well, the easiest way to indicate that is to have it as null. Okay, so we have a block, and the question is, what is a statement? What is a bang statement? So we can have different kinds of statements, right? We can have different kinds of statements, but right now we have only one kind of statement, which is an expression, right? And that expression simply performs a side effect, right? Right simply performs a side effect. So let's introduce something like type def struct, and it's going to be a bang statement, right? Since we're going to have only one kind of statement right now, we're not going to even have anything like bang statement kind to distinguish between different kinds of statements. It's just a waste of time. We're going to have just this. And expression, I think I said that we not going to reuse AST of bosom, but then I just realized that we can reuse the expression part of the AST of bosom. Let me see if we can easily do that. So there is expr, yeah, and we have a lot of things in here. For instance, we have bindings, right? Particular like name variable. I think these things should be called variables, but we can call them bindings. So we have different kinds of literals: integer, float, character, string literals. We have binary operations and function calls, and we do have a function call in here, and function call accepts a single string literal. So that means we already should be able to parse this line. We already have a parsing for this line for free, essentially. So that's pretty cool. This is precisely why I didn't want to start this thing from scratch, and I just want to reuse part of the bosom, because yeah, I can just reuse expressions, because our expression parser is actually quite cool. Why not just reuse it? So okay, let me actually include something like expr.h, and here's an expression. So this is going to be our bang statement. Here is going to be our bang statement, man. Okay. So that's pretty much it. So this is the entire AST that we need, and we just need to implement a simple function, right? This function will accept the tokenizer, and return a bang proc def. So I think it should be called parse bang proc def, right? So that's how it should be called. It's going to be false, parse bang proc def. We can put it as a to-do. To-do is not implemented. There we go, there we go, and this entire thing is going to be just like zero initial. I don't know if it's needed because assert is a no return function, so maybe majority of the decent compilers are going to be okay with that, except one, of course. All right, so let me recompile this entire thing and see what's going to happen. Okay, so we have a bang block, and oh yeah, we're self-referring to this entire thing. So I think the easiest way to actually go about this kind of stuff would be to do something like this: type def struct bang block like this. Is it going to work? Hopefully, we'll see. So this function has no prototype. Let's actually mark it as static. Do we have anything else? Okay, and we have unused variable in here. Let's actually mark it as void for now. Tokenizer. Tokenizer, and this one is just unused. Okay, so I guess that's pretty much it. The next step that we want to do in here, right? The next step that we want to do in here is parse this entire thing, right? So we've got a tokenizer, and the next thing we need to do, we need to parse the proc definition. So it's going to be something like proc definition, and I'm just providing the tokenizer to pass the proc definition, right? And after that, I want to be able to, like, you know, dump this proc definition as AST. So maybe I'm going to do something like dump proc definition as dot edges. So that's one of the things I can do. Proc definition. So I'm just dumping it as a dot edges so I can visualize it with the graph viz and see what's going on in there. Yeah, this is one of the things I probably want to do. So, but to be able to do that, I think I need to wrap it into like a graph of some sort, and this one is probably has to accept stdio. Right, so this one can be dgraph proc def like this, and this has to have a new line, and this one has to have a closing curly brace, and there we go. We only need to define this function somewhere along with this kind of stuff. Right, so it's gonna be static void. This one is going to be file stream, and this one is going to be something like bang proc definition. Do I want to pass it as the pointer? I can pass it as the pointer, why not? But what's the point? I don't know, I can pass it as the value, to be fair, for this specific case, proc def, right? Just pass it as the value, so it has unused arguments in here, so proc def, assert false to do dump, and to do is not implemented. Is it gonna work now? Let's see if it compiles or not. Okay, so a couple of warnings and shit, and yeah, so we have unimplemented parse bang proc def. All right. So first thing, when we started to parse the proc definition, as we already established, starts with a proc keyword, right? It starts with a proc keyword. You know what? I'm gonna actually color it with the nim mode because it does have a proc keyword, so this kind of stuff looks a little bit nicer. You see, now it looks like a legit language, is it not? Look at that. Look at that legitness. Look at that legitness. Yes, 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 yes. All right, so how we check if it starts with a specified le token? So I think we have a special function for that, right? So it's called expect token next. You provide a tokenizer, you provide expected token kind, and also you provide a location. But since we don't really have a location, we probably have to provide a dummy location. But it's going to be fixed later, of course. Of course. Trust me, I know what I'm talking about. I'm going to fix that later. All right, so expect token next. We provide the le tokenizer, and expected token kind is going to be token kind proc, I suppose, right? Token kind proc, and I'm gonna put a dummy in here, so it's gonna be file location dummy, file location. As well, actually, this one could be just like 0 initialized, right? It's just like a dummy location, whatever. So we expect a next token. Let's actually see if it will break or not. And this thing is supposed to return the this thing somehow. So maybe I'm gonna do proc bang proc definition result, right? So this is a bang proc definition result, and I'm gonna just return this entire thing. Oh boy, oh boy. And of course this thing is not 0 initialized. I forgot to 0 initialize this thing. One more time. One more time. Okay, so now it fails at me trying to print this entire shit. Oh boy, printing AST as dot graphics is always a huge pain in the ass for some reason. So I don't know if I want to do it right now, but maybe I should do it somehow. Because it involves the generating unique IDs and stuff like that. So the question is, do I really want to do it? Do I really want to do it? Maybe I do, maybe I don't. Who knows? Maybe I can just take a look at the at this thing inside of a compiler. That would be nice, actually. Maybe we can just look at that inside of a compiler, right? Before trying to evaluate it, just like put it in here, bang.c, and just see what we have in there. So it's the line 112. Okay, so we can try to do that. Why not? So it's going to be something sodding bm, right? Sodding bm, and I'm going to just be running toolchain bang. So here is the bang. I have to provide main bang. Is it going to be working? Yes. Okay, gdb. So I'm going to break on main.c 112. Okay. Are you telling me? Oh, it's actually called, it's just called bang, it's not called main. I see. I see. And what I need to run it with? I need to run it with main bang. Okay, so now I can try to print proc definition and see it's 0 initialized. Okay, that's, believe it or not, that's precisely what I wanted to see. That is precisely what I wanted to see. So I'm gonna go to here, and then the next token we expect is the name, right? That's the next token we expect in here. So it's gonna be name token, right? It's gonna be name token. Expect token next, tokenizer, token kind name, and we provide a dummy location. We just provide a dummy location, and in here we're going to be doing what? You know what? I think I can. So we only need to extract the text, so that means we can assign something like this. Proc, result name is going to be equal to that, and that's it. That's actually pretty cool. So the next thing we're going to be expecting kind open parent, and then we're going to be expecting closing parent, right? So if you take a look at the source code, all right, so here's the proc, then the name, open parent, closing parent, right? So, and after that, we're going to be expecting open curly, right? And after that, I guess we're going to be parsing. I don't know, man. Maybe we actually should not expect a curly in here, and we're gonna have a separate function for parsing blocks, like curly brace blocks, if you know what I mean. Yeah. So let's do it like this. It's gonna be something like result body parse curly bang blocks. Bang block, and we're gonna just provide a tokenizer in here, tokenizer, and there we go. So, and let's actually, I mean, what the hell am I doing? So this is gonna be a separate function that parses all of that. It's gonna be static bang block, right? It's gonna be pointer, tokenizer, right? right? And for now, it's gonna just return null, right? It doesn't really matter that much. All right, and here we're gonna be doing like we're gonna be expecting the open curly brace, then we're gonna parse everything until we see the closing curly brace, and then the whole block is gonna be returned to here, and that's gonna be pretty much it. So let's see if this entire thing compiles. Right, let's see if this entire thing compiles. So there's something overall, yeah, it compiles, it fails at trying to print all of that, so let's actually remove this thing. So what's the stuff? 1 2 1 break bang C121, right? So this is gonna be that, and we're gonna run it with main bang to name. Okay, and let's actually print proc def. There we go, and as you can see, we actually managed to parse the name. Right, so the data points at the beginning of the source code and the count is 4, right? So that means the actual size of the string is 4, so everything else is going to be actually ignored. So, all right, so we managed to parse the name of the procedure, at least, which is already kind of cool. But the next thing we need to do, we need to parse the curly bang block. Curly bang block, and I'm just realizing that to do that we'll need arena, because we're going to be allocating the nodes of the linked list we are appending to. Right, that's precisely what we need to do in here. So it means I need to accept the arena pointer in here, the arena pointer, and so that means I also have to accept the arena in here. Right. Arena like that, and in here we're gonna be passing the arena like that. So let's actually go through the compilation errors and fix all of that. Right, so here's that, and this is gonna be pointer to arena. Is it gonna be compiling? Is it gonna be compiling? Hopefully it will. Right, and there we go. So first we expect token next, right? So we're gonna provide the tokenizer, and the next token is going to be token kind curly open curly, right? So it has to be open curly. We're gonna be ignoring it, and then we need a closing curly, right? So here's the closing curly. So the next thing we need to do, it's actually rather interesting. So I suppose we need to parse expression. We need to keep parsing expressions until we encounter closing curly. I think that's precisely what we need to do. So let me see. So we're gonna have a token, and in a tokenizer, token next, we can take a token peak. Yeah. So what we need to do in here, we need to do like a token peak, right? So we provide the tokenizer, and then we provide this entire thing, and then we need to provide some sort of location. This is a dummy location file, location dummy. It's just like 0 initialized. It doesn't fit into our entire scheme, but in any case, while you have the next token and that token is not equal token kind closing curly, right? So while you have the next token, that token is not closing curly, you keep parsing the expressions, right? And as I already said, we have a special parser for the expressions. So parse expression from tokens, that's precisely what we have in here. And this entire thing accepts the arena. We do have the arena. It accepts the tokenizer. We do have a tokenizer, but it also accepts the file location. It shouldn't actually do that, but it is what it is. Okay, so here's our expression. Here is our expression, and we need to append that expression to the linked list, like block of some sort. So we're going to actually have something like bang block. So this is where the block begins. It begins at null, right? And then we're gonna have a bang block, and this is where it ends because we're going to be appending to the end of the linked list, right? So this is basically what we're going to have in here. So after everything is done, we're going to be returning begin, and we're going to forget an end. All right, so we've got an expression and shit like that. So, and a single statement. All right, so maybe we need to do something like bang block. All right, so we have a bang block, and I need a name for it. So it's like let's call it a node. I have no idea, but I just need a name for this thing. So I'm going to be allocating arena size of node. Right, so just need to allocate this entire thing. Bang block, and of course this actually has to be like this. Right? So I've got a node, and then I need to do something like node statement, and in the statement we have what? We have expression, so it's going to be expression. And maybe I can allocate it before I try to parse this expression, so I can assign it, write it into the node itself. Okay, we've got a new node, which is cool. So now, if end is not equal to null, what I'm going to be doing, I'm going to be setting end next to the node and end equal to null. So basically appending everything to the end. If end is null, that means begin should be also null, right? Begin should be also null, right? And what we're essentially doing, we're just assigning begin to end to node, right? So we're assigning node to end and to begin, and just you know, initializing everything. So that should be all right as far as I can tell. And after that, we should expect the semicolon, right? Because the statements are going to be ending with a semicolon, right? We're going to be ending with a semicolon, and after that we're ending with a closing curly brace. And believe it or not, I think that is it. I'm pretty sure that is it. Do we need anything else? I'm not sure. Okay, let me see. Okay, so we've got that. Expect token next. Too few arguments. Okay, so you also have to provide that token in there. So let's provide it. You have to provide the dummy location. I completely forgot about that. So this one is going to be dummy. Completely forgot about all of this stuff. Dummy. All right, it compiles, but now we need to implement the printing for this thing, and I'm not sure if I want to implement printing because it produces pretty pictures, but it's not really getting us super close to the completion. So I'm not really sure if I care about it, to be fair. So let's actually check if we parsed everything correctly inside of the debugger. It's just gonna be easier. So let me take this stuff. I'm gonna just break this entire thing, and I'm gonna run main bang, and let me enable this thing. So I'm gonna print the result. It should be 0 initialized. Then I'm extracting the name of this thing, so the name is extracted successfully. And let's take a look at the body of this thing. So the body does have some sort of a pointer. Let's take a look at that body. So here's the body, it is the pointer. Let's dereference that pointer, and inside of this thing we have an expression that is a function call. Would you look at that? We do have an expression that is a function call. So if I take a look at the statement, okay, so it has to be something like this, I suppose. Okay, here is the statement. Inside of the statement, if I take a look at the expression, and then it's a function call, so that means I should be able to do something like as fun call. It is not called fan call. Oh, it is very interesting. So maybe because expression Has to be like this. Yeah, first you have to take the value, and inside of that value you can do as fan call, and here is your fan call. If you take a look inside of that fan call, you will see that the name is right, and you have a bunch of arguments in there, right? So you can take a look at the arguments. Inside of that arguments, you will see that you have a string literal, right? You have a string literal, and maybe you can even take a look at as lit str, and I don't remember, so it has to be value, I suppose. Okay. So this is the args, then as maybe you have to do value. Okay, here's the value. Inside of that value, as lit str, but here it is, and not least, lit. Okay, as lit str. There we go. Yes, here it is. So we went really deep down into the body. We found a statement, then expression of that statement, then we figured out that it's a function call. That function call has these arguments, and this argument is a string literal. We successfully found that. That's actually pretty cool. That is actually pretty cool, and we partially reused the parser from Bosom. Okay, that's pretty cool. So we should be able to now iterate through this entire stuff and maybe do something about it. I don't know. Can we reuse Bosom context for this kind of stuff? I think we should be able to reuse a Bosom context, if you know what I'm talking about. Because in the Bosom context we are we have the program area, right? So it's going to be library Bosom 2. We have a main program area. So here's the main program area. We have different program locations and whatnot. This is where we're going to put in instructions. We also have an entry, right? We also have an entry, and we also have strings and whatnot, the memory and stuff like that. And when after everything is done, we can simply dump this program to the standard output. So maybe we can reuse Bosom for all of that stuff. That would be actually kind of cool. And on top of that, Bosom, as you can see, has its own arena. Right. It has its own arena, so we could have reused the arena of Bosom. Right. So when we emit an instruction, right? Bosom, let's see, emit instruction. So because we'll need something like this when we're working with all that. So emit instruction type, you provide the location for this thing, then we take a look at the definition, and then we take a look at the, and then we put push a deferred operands. Okay, I see. So maybe we should not do emit instruction, we should rather look at the deferred operands of whatnot. So it feels like we'll need to separate Bosom into context that generates new BM program and the context that is needed to maintain the logic of Bosom. So it feels like since we're introducing a new language, Bosom entity is actually two entities smashed together, because part of this thing wants to be reused for Bang. Okay, this is a very interesting information. This is very interesting information. All right, so let me try to do something now. Okay. So maybe I'm gonna remove the dump thingy because it's not particularly useful for now. So let me go through this stuff. I don't need that stuff anymore. Okay. So we have arena. Let's actually allocate something like bosom, but I'll also allocate it in static memory because bosom is actually pretty big structure. I think it may actually destroy our stack. Let me see how big it is. Doesn't really compile, of course. So we need to include bosom just to be able to use all of that. Yes, bosom the page. Are you gonna print me the size? This is the size of this thing. This amount of kilobytes is just like 1 megabyte. Yeah, so the size of the whole bosom structure is actually quite big because it like has arenas and shit, and also it has like memory sections for different programs and whatnot. So it's a pretty big structure. It's better to allocate it in static memory just in case. But what's interesting is that this structure 0 initialized is a valid bosom state. It is in fact a valid bosom state, so you don't need any initialization here. That's actually pretty cool. All right, so let's take a look at this stuff. Arena, so it has to be bosom arena. So everywhere we use arena now, I just have to prefix it with a bosom arena. And how many of such places do we have? Not that many, to be fair. Not that many. So we have this thingy. Okay. Another one. Okay, so bosom arena free. Maybe it's not even that important. Come on. The operating system is gonna clean everything up for you anyway. Right. So now. Now I need a function. Now I need a function that would accept the whole bosom context and my bang proc def. Right, so it's going to be proc def. And it will generate some stuff into the bosom. That's going to be the idea essentially. Let's call it something like compile proc def into bosom, right? So, and I don't think it should return anything. It just takes bosom and proc definition and simply compiles that proc definition into bosom. Simple as that. As simple as that. So interestingly enough now, how are we going to compile all of this thing? So there's no operation that appends like an instruction into the bosom, because that's precisely what I want to do in here. Like I want to append an instruction into a bosom. I kind of want to make a cup of tea, so that's probably what I'm gonna do. So the first thing, we also need to ensure that BAMS doesn't have an entry point, right? So we should ensure that has entry doesn't have an entry, because we're gonna add the entry. And the entry that we're gonna add in there is gonna be bosom entry is like the current program size. The current program size is gonna be the entry now, right? Bosom program size. So here is our new entry. Right, that's what's going to be, because you provide the procedure and procedure becomes the program that you want to use in there, right? So after that, do we need anything else? I don't think we need anything else. We just need to start, you know, compiling the statements, right? So maybe we can do something like compile block into bosom, right? So we have to provide the bosom, and we take the proc definition. I don't think it needs to be like a pointer, to be fair, right? And we take the body of the proc definition and we compile this entire thing into the bosom, and that should be it. I think in terms of like for this particular procedure, right? For this particular procedure, that should be it. So then we are compiling this thing into that. So this is going to be bank block right? And in here, while block, we're going to be compiling statement into bosom. That's what we're doing. We're compiling statement into bosom, right? It's going to be block statement. There we go. And this particular function, and of course, maybe after that we have to do something like block next, right, until we exhausted all of the blocks. And this entire thing is going to be static void. It's going to be bosom, and it's going to be bang statement, right? So it's going to be statement, and the statement is just an expression, right? So it's going to be just an expression. And this one is going to be very, very interesting. So again, we're probably going to do something like compile expr into bosom statement expr. And the reason why I'm creating so many layers of the function is because in the future these functions are going to be bigger, right? It's just like we're implementing the bare minimum of the compiler, the bare minimum. But we also think about the future, how it's going to extend in the future. So bosom, so this is expression, and depending on the type of the expression, we're going to do different things, actually kind of the expression. So it's going to be expr kind, and what sort of kinds do we have? What sort of kinds? Let's let the compiler tell us all of that. So is the compiler going to tell us all of that? So here are all of the kinds as far as I can tell. Okay, good. So can I just remove this thing and just take all of that here? There we go. Maybe now I should be able to do something like this. And then it's going to be case. And for that specific case, we're going to have something like this. Can your Vim do that? I don't think so. All right, so here are the things. What we need support for. Right now, we're going to be only supporting lead str and function calls. Everything else is not supported yet. So, so we're going to do something like false compilation of this kind of expressions is not supported yet. Right, and we're also going to exit with 1. There we go. And here what we need to do in here. So we need to be able to compile a string, and we also need to be able to compile a function call. It's as simple as that. So compiling the string is rather interesting because that means we'll have to add the string to the memory, right? We're adding the string to the memory. And then we're using its result as the command line arguments and whatnot, right? So that's what we're doing in here. So, okay, can I actually inline this entire thing? I think I should be able to. So when we encounter lead str, right, lead str, bosom has a thing, something about memory. Push string to memory. Yes, that's basically what it has. push string to memory. So we can provide the bosom, and then we take a look at the expression, right? Expression is lead string, so we take a value as lead str, and there we go. We're pushing this thing into the bosom memory, and we get str address, right? So we've got an str address, and we need to be able to push a new like instruction into bosom. So let's actually do something like bosom push instruction, right? Push instruction, and instruction what I want to push in there is going to be I don't know, instruction push, and what I want to push in there is the string address. I want to be able to just generate things like that, right? You see what I'm talking about? I just want to be able to generate things like that. All right, so, and that's pretty much it. So that will compile down to just pushing this thing there. And function call, okay, let's take a look at the function call. So if expression value as fun call name sv equal, if it's equal specifically right, if it's equal specifically right, we need to implement that. Compilation of write function is not implemented yet. Otherwise, if it's something else, it's just like unknown function. Right, so this is a known function. So how can we're gonna compile write? First of all, I think in bosom we probably need a way to actually add external natives of some sort. How do we translate natives though? External natives, right? Translates a native statement. Okay. I see. Okay, that's very interesting actually. Native name. Maybe we need to have a separate function that lets you push an external native into the bosom, and that's precisely what we probably want to do in there, right? External native. So do we even have anything else for that? I don't think we even have anything else for that. We only need like a location or whatnot. Location whatnot. I'm kind of a little bit lazy to implement that because I mean I'm actually getting tired. That's probably why I'm getting lazy to implement all of that. And this kind of thing should be actually implemented before we're trying to compile anything, right? Before we even trying to compile anything at all. So let me see. It's going to be bosom push external native. Right, so we're going to provide the bosom, and the native name that I'm going to push in there is going to be right. So we're expecting right in here, and then I should just compile proc definition into bosom. Right, that's precisely what I'm doing in here. Proc definition into bosom, and here is the proc definition. All right, and after that I should save the executable save file as bm. What's cool is that I can probably save it as nasm csv as well. So yeah, but for now I'm gonna actually save it as bm, and the place I'm gonna save it to is actually known. It's an output file path. All right, so that should be the final thing in here. That should be the final thing in here, and what I'm doing here, if it's a write function, right, if it's a write function, it actually quite, interestingly enough, it depends on the index. So what's the index of the native? Type native ID, location, external size. So this function, push external native, so do we have a type native ID? we should have a type native ID. Native ID, write ID, right? So this is what we're gonna have in here, and when we're compiling this entire thing, we have to actually provide this write ID in here. Otherwise, we won't be able to compile that. So it's gonna be native ID, write ID, and we're gonna be passing that everywhere, as far as I can tell. Oh boy, so it's gonna be write ID. So this one is gonna be something like that. It's gonna be write ID. It's native ID, of course. Native ID. It's gonna be write ID. It would be easier to actually make it a global thing, but again, it's not really global, if that makes any sense. So let's just pass it around. Right ID, and here is the right ID thing. Is the right ID. Now, if I encounter this kind of thing, the only thing I want to do in here, I want to just push the instruction, bosom instruction native, and the value for that is a right ID. That's it. Believe it or not, that is it. Yeah, precisely. So, but it's not going to compile because we need to implement at least two functions in here. Bosom push external native and bosom push instruction. Let me actually try to compile this entire thing and see if I'm right. So yeah, we don't even have a native ID, but we do have instruction address, right? We have a type def instruction address, right? So here it is. And another thing that we need to have is a native ID, right? Because it's also part of the virtual machine. And native ID is basically our FFI. Okay, so we don't have a bosom push instruction, but we need to implement it. We just need to implement it. I wonder how we can implement that. I think maybe I can just implement it in here and then move this entire thing to bosom later, right? I can move it to bosom later, and this is instruction. This is instruction kind, I think. Is it instruction? It's instruction type. Okay, inst type. And this is the instruction operand. Right, and now if I want to push an instruction into bosom, right, if I want to push an instruction into bosom, what am I doing here? First I want to assert that I can even do that, right? So it's a bosom program size less than BM program capacity, right? So here it is, and then bosom program, it's going to be something like that. Maybe. So if it's an instruction, I forgot the definition of instruction. It's located in BM, so it's a type and operand. Okay, so it's going to be type, inst type, and operand, inst operand. Should be all right, and after that I should be able to just +1. Okay. So we also have like program locations and whatnot, but I think we're not going to fill them in for now. Not gonna fill them in for now. So this is the push instruction. Do we have anything else? We need external. Wait. Function is a pointer. Did you mean to use? Yeah, probably I meant to use that. Sure, why not? Okay. Write ID. We don't have a write ID. Or push instruct. Okay, so word U64. That's what's needed here. Word U64. Okay. Oh, in a write function is going to be actually something super okay. So implementing write function is not as easy as that. So it will require also checking arguments and stuff like that. So it's going to be a little bit more painful than that, but okay. So yes, of course, it has to be a pointer. Push external function, we don't have that. Let's maybe implement it. Push instruction, static void, bosom, native name, and let's actually steal some code from there. So it's a native statement, and that is precisely what I'm doing in here. So I'm just doing mem copy, and then I'm going to be incrementing external size and returning a new thing in here, but maybe also have to return native ID. Right, so this entire thing is going to be native ID. Native ID result is going to be equal to simply that. And I'm just going to be returning results. There we go. So we also have a name. So I just mem set it, then I copy native name to that, and then just increment all of that. So that's precisely what I'm doing here, I think. I think that's precisely what I'm doing. Is it going to be working? Is it going to be twerking? I think it just compiled. So here is a little bit more complicated, of course. This thing is a little bit more complicated. What we need to do in here is, first of all, we need to check the arity. Right, we need to check the arity. So in expression, arity. Okay, we can do something like expect arity. Yeah, I think this is the easiest way to go about it. It's going to be a function call. Right, so this is a function call. Expected arity, and it's going to be 1, and file location is going to be just dummy. So it's going to be a dummy file location. And a file location dummy, and we're gonna zero initialize this entire thing. Alright, so we checked the arity, expect arity, so we're gonna have a yeah. So the next thing we need to do, we need to actually evaluate this entire stuff. Right, we need to evaluate it. But to be fair, what does it really mean for us to evaluate this stuff? Well, for us, evaluating this thing is essentially means compiling it down, I guess. To be fair, when we're compiling the string down, we're not only pushing the address, we also need to push the size of the string, right? I guess that's what we're doing here. So I'm pushing this, another instruction is going to be instruction push, and what I'm pushing in here is just word use64. So this thing, right? This thing as count, right? So I pushed two things in there, like a string and the size of the string, and then I can call write syscall. First, I probably also need to compile the expression. So I'll have to compile expression into bosom, providing the bosom, and expression is going to be expression value as fun call args, and args value. Right, so it's going to be args value. And suppose it is an expression. So after we compile this entire expression, we're going to be pushing this thing, and it should be okay. It should be okay. So is it going to be compiling now? Bums, bams, bams. Let's get that damn spam. Okay, so where is this function located? Is it an internal function, really? It is in fact an internal function. Why do I hide this? It should be available for everyone. Bang bang. Okay, so compile expression into bosom, and too few arguments. So what else? Yeah, it also expects write ID. Okay. It also expects write ID. Okay, I think we got it. I think we actually got it. Oh my god. What the fuck? Did I just implement? Okay, let's actually remove all of this stuff that is not needed. So we have only main bang. So here's the main bang. And can I try to compile this entire thing? So I'm going to do build toolchain bang. And I'm going to just provide bang. And it did a thing. And here is an executable. Let's try to disassemble that executable. Can I do debusm? Debusm of that executable, of that BM. And this is what we have in here. We have a push 0, which is probably the address of this instruction, and then push 12, and then native. And here's the one thing that I noticed. We don't halt the machine. So maybe after we compile this thing into busm, we need to do something like busm push instruction. So we just push instruction busm, and what instruction we push in there, we're going to be pushing something like instruction halt, right? And halt doesn't have any operand. We can just do something like word u64, right? And let's see what's going to happen. So might as well. So let me take this thing and just put it like that. And maybe also I want to do no build test just to, you know, rebuild everything just in case. And there we go. We've got a program that actually also holds. So it pushes the address, it pushes the size of the entire thing, and then it runs native, and everything should be Gucci. Everything should be Tamaguchi. We can take a look inside of it. It has hello world and write, and let's try to run this entire thing. To run this entire thing, we'll have to run toolchain BME, and let's just do something like hello BM. And that is really strange, but it printed this. Oh, this is because it's a wrong one. It has to be main BM. Yeah, there we go. Now it printed hello world. Yes. We implemented a compiler that can only compile this program. Let's actually change it and demonstrate that it actually like works. Let's actually say hello bang. Hello bang. So, and then let's try to recompile this entire thing. Right, so I mean, I'm recompiling the whole tool chain, right? But then I can try to run this entire thing, and it says hello bang. Would you look at that? Yes, you can change this string and it will change its behavior. Furthermore, as far as I know, you not necessarily have to translate it to file as BM. We can actually translate it as assembly. Did we just create a native language in 2 hours? Holy fucking shit. Okay, so let me see. So it's gonna be a library. So it should be somewhere in toolchain busm.c. And since we're doing Linux, we're going to be generating it like this. So where's bang? All right. I'm going to do something like this. And this is going to be the thing that we're generating in here. All right. So let me go to here and recompile this entire stuff. All right. And I'm going to be just, you know, saving all of that. Okay, so do we get it should have actually, okay, so it probably saved it. Oh, okay, so it saved it to BM. All right, so it just saved the assembly to BM. All right, this is actually pretty straightforward assembly. And we can try to compile this entire assembly. So I don't remember how to do that. I think we have no build.c, nasm. We have to call, let me see, so it's going to be build toolchain. Yeah, we have to call nasm f nasm f elf64. And we compile in main.bm into main.o. Is it gonna work? I think it worked. So now we have an O file, and now we have to do something like ld main O, and we are compiling that into a main. Okay. All right, and we've got a main, which is a statically linked executable, and if I run this entire thing, it says hello bang. Yes. So our system generated assembly that we can compile down to native executable, and there you go. This is a native executable pretty much generated from this program, and I did that in 2 hours. So yeah, that's pretty cool. So yeah. All right. So I guess this stream was pretty productive and educational, at least for me. And it's essentially a pivotal point in development of Bosom, because we're trying to stir the development of that entire thing towards like a proper programming language, and the virtual machine that we developed for this entire project is going to be basically intermediate representation for code generation and whatnot. And as you can see, it's working. It is actually working. You can just generate native executables and whatnot. So thanks to everyone who submitted who contributed to the native code generator, because I only wrote like a code generator partially. So other people contributed to this code generator, namely Heroes and Plots and Bitstream. So yeah. But yeah, that's it for today, I suppose. We implemented a hello world of compilers. We implemented a compiler that can only compile hello world and nothing else. And I guess on the next streams, we're going to continue developing these things and making it more powerful and refactoring everything and just reorganizing. But for now, we have this. We have a compiler that can only compile hello world programs. Furthermore, I think, well, right now you can actually do that at least 5 times. It should be possible to do that 5 times. We don't have loops yet, but we will have them in the future. So let me actually rebuild everything. Right, so there's something wrong with the compilation. Like it keeps, sometimes I accidentally save compilation buffer and it keeps saving it. Emacs is weird, like honestly, Emacs is weird, but anyway. So I recompiled this entire thing, so now we should have 5 instances of printing hello world, I suppose. Don't really see that though. Did it actually become bigger? Maybe. But we have a memory like in here. Okay. Oh. Okay. So let me see. I'm gonna actually generate a bytecode because it's a little bit easier to work with. Right, it's a little bit easier to work with. So I'm gonna rebuild everything, no build test. No build test, and I'm gonna do a bang, and in BM we have just this thing, and maybe we can even try to disassembly this entire thing. So it's gonna be debusm BM, and as you can see, we're actually, well, this one is interesting, is I think it will just push the string several times. Yeah, so it actually, yeah, it actually, excuse me, it actually pushed the same string like 5 times, but I mean, it technically, like, it will work, more or less. So, and if I run it, it will print hello world, but without any new lines. I don't remember if our parser supports new lines. Let me actually see. So it has to be, let's use new or something. Yeah. Okay, so let me see. So it's gonna be bang, and then I'm gonna do debusm, so it does work correctly, and there we go. So we have a 5 hello bangs. So it's not just like hard-coded, right? So we do parse the sequence of statements correctly, right? We do parse them correctly, and we compile them accordingly. So we don't reuse the same string literals, but maybe at some point this is something that we're gonna implement anyway. That's it for today. That's it for today. Thanks everyone who's watching right now. I really appreciate it. Have a good one, and I see you all tomorrow. Tomorrow, according to the schedule, we're gonna continue developing this thing and making it better, making it cooler, and maybe one day everyone is gonna program in Bang. I don't know. Is that a good name for a programming language? Maybe it's not. Anyway, that's it for today. Thanks everyone. Love you.